Where am I? Why am I here?
Tell me everything you know.
I have no idea what you're talking about, man. I'm innocent.
Well, hold on. Maybe this is gonna ring a bell right here.
I don't know what to tell you. I've never derived this equation in my life.
Now hold on, don't you lie to me. We found this on the interior and on the boundaries of your residence. What is this thing?
Okay, you caught me. This is my equation.
Well, actually, this is a second order differential
Hold
equation.
on, bro. I don't understand your yapping here. So, I'm gonna have you use this whiteboard right here to explain all this.
Wow, that's a big whiteboard. Well, let me break it down for you.
First, we can look at a relatively simple example of harmonic motion, a pendulum. Here we can see the pendulum as it swings, and it has an equilibrium point. If we graph this equation, we can see that the equilibrium points are simply where the second derivative is equal to 0. But now when we take a more complicated example, like this sound wave, when we plot it out, the equation is much more complex. So a simple calculus won't do, and we need to use my equation, the Laplace equation. First, we can use the force of gravity to solve for our equation. The force of gravity is equal to the gravitational constant times m times little m over r squared, where r squared is the distance between the two objects squared. On Earth, the acceleration due to gravity is simply m times g. We can cancel out the m's and we can solve for g, where g is equal to big G, the gravitational constant, times m over r squared. We can also turn these all into vectors by multiplying by the directional vector u. Now, we can convert this to a Cartesian plane by defining phi, where phi is g times m over r. Phi is actually a function in 3 space, so it actually has the parameters x, y, and z. Furthermore, this also lets us take r and reparameterize it in terms of x, y, and z, where r is equal to the square root of x squared plus y squared plus z squared. Now, we can find the del operator, or the gradient of phi, to see how phi changes for every value of r. The gradient is simply negative g m over r squared via power rule. Now, using the rate of change of phi, we can plug this in back into g. G is equal to the negative del operator of phi times the directional vector. However, what I want to know is the rate of change of g, so I can figure out where g has equilibrium points, as in where our equilibrium is stable. So, in order to do that, I'll find the del operator or gradient of g, and that will give me, on the right side, the negative del operator of the del operator of phi times u, which is our direction vector. So we get the second order del operator, which is often called the Laplacian operator, named after myself. Now, using this gradient for g, we can find the equilibrium points where the del operator of g is equal to 0. Given that u is simply a vector, that means that we need to find where the del operator, or the Laplacian operator of phi, is equal to 0 in order to find where the del operator of g is equal to 0. Now, we can find phi squared, or express it as simply a chain rule, where the derivative with respect to phi over the derivative with respect to r multiplied by the derivative with respect to r with respect to x, y, and z can be expressed as a total function. Next, we can also simply find our second order differential by plugging in for r, so that we get g times m over x squared plus y squared plus z squared to the power of 3 over 2. This tells us that when this function is equal to 0, we can find the x, y, and z coordinates where our point of equilibrium stands. But we also know that distributing out the chain rule, we can see that we get the Laplace equation, where we get the second order differential of phi with respect to the second order differential of x, y, and z equals 0, and therefore is a point of equilibrium.
And that's why my equation is the greatest thing ever. Did you catch all that?
What? Oh, yeah, I got all that. I got all that loud and clear, sir. I'm gonna go check with my detectives and I'll get back to you about it. Yo, IT dude in the corner.
I told you for the last time. My name is Anand.
Well, it doesn't matter. You're still the IT department. What do you got on this dude?
Well, you see here, he's a ghost. There's no information on him. But I found something. He's connected to an old friend of yours. Well, for that, I'm gonna need something a little extra.
Come on, you and your old habits. So who is this dude?
His name is Frederick Gauss.
Oh, not Frederick Gauss again. I've been trying to go after that guy for the last 20 years. Okay, so our suspect here showed us that Laplace's equation looks like this. It's the second partial derivative with respect to each term, and the sum of them equals 0, or the Laplacian operator equals 0. Let's see how this applies to Gauss's law. Gauss's law in its most simplest form just says that the electric flux in an electric field equals the total charge Q divided by the permittivity epsilon naught. This is the version of Gauss's law that's in your AP Physics formula sheet. The differentiable version of Gauss's law says that the integral over a closed surface of the electric field vector with respect to the area vector gives you the electric flux in that field. Now we take the integral over a closed surface because an electric field is a closed surface. I draw my electric field here, and each of those green dots represent charged particles. Also, if I want to use Gauss's law, I need to assume a uniform charge density in my electric field. That is one of the conditions that must be met to use Gauss's law. I'm going to make some substitutions here into these two equations. I'm going to write my charge density rho equals my total charge Q divided by the volume of my electric field. My charge density equals total charge divided by volume. I can rewrite this as an integral to say that the total charge equals the integral of my charge density with respect to volume. Using this information, I'm going to substitute this into the left-hand side of the equation for total charge, and here's what I get. Now, I'm going to use Gauss's divergence theorem to make a substitution on the right-hand side. Gauss's divergence theorem says that that thing on the right-hand side, the closed integral of the electric field vector with respect to the area vector, that just equals the integral of the del operator dot the electric field vector with respect to volume. Those two are equal, so using this information, I'm going to substitute that in on the right-hand side to get this equation at the top right here. This is a much more simplified version of the original integrals, and look at that, they both integrate with respect to volume. Using the laws of calculus, I'm going to manipulate this a bit. I know that the del operator dot the electric field vector is a constant. It's a dot product, so I'm going to pull that out of the integral. I'm going to bring epsilon naught, my permittivity, to the left-hand side, and I'm going to pull rho out because I know that charge density is a constant on the right-hand side. The two integrals cancel out because they're the same term, and now I'm left with this. Without those two integrals, I'm going to rewrite this to say that the del operator dot the electric field vector, the dot product of those equals the charge density divided by epsilon naught, the permittivity. Now, to simplify that, I'm going to use one of Gauss's other laws, which says that the electric field vector equals the negative del operator times the electric flux of the electric field. I'm going to substitute that in for the electric field vector, and now I'm left with the Laplacian operator times the electric flux equals the negative charge density over epsilon naught. I'm going to make the charge density arbitrarily equal to 3 for this example because at a certain position in that electric field, the charge density could be 3. Well, in order for Laplace's equation to be met, the charge density at a certain position must be 0. So Laplace's equation is met when the charge density at a certain position is 0. Now that I've proved that Gauss's law comes from Laplace's equation, I can use Gauss's law to find positions in the electric field where the electric flux is not changing. I can find where the charge density is not changing. I can find these positions in the electric field with Gauss's law because I know that Gauss's law obeys Laplace's equation. It's like your equation's got a ton of solutions, man. You know, it has the potential to revolutionize fluid dynamics, rocketry, heck, even electromagnetism with Gauss's law.
Does that mean I'm free to go?
No,
Aww.
because when we raided your house, we also found that you've been evading your taxes.
My taxes? I thought I optimized for that.
Well, look, just because your equation equals 0 doesn't mean you can pay 0 in taxes.